This lecture is on invertible linear transformations. As you studied in pre-calculus, calculus, you know that a function is invertible or has an inverse if and only if the function is one-to-one and onto. So it's the same here. We're looking at these transformations not as matrices, we're looking at them now as mappings. And T is invertible if there exists a transformation U such that U takes W to V, and if we compose them, UT is the identity transformation or the identity function on V, and TU gives you the identity mapping on W. In this case, we say that U is T inverse. This is exactly what you have known about functions. You know that a function has an inverse if and only if it is both one-to-one and onto. Now, recall that if V and W are finite dimensional vector spaces, and if they have equal dimension, then there are four ways that you can say the same thing. T is one-to-one means the same thing as T is onto. The rank of T is the dimension of V, or the nullity is just the zero vector. So any one of these will give you the fact that your linear transformation is invertible. Here's a very simple example. T is a linear transformation taking the vector space of polynomials of degree 1 or less to R2 by T of AX plus B is the ordered pair A, A plus B. And in that case, T inverse, you could work this out yourself, T inverse would take R2 to the space of polynomials by, well, it takes an ordered pair CD, and it gives X the coefficient C, and its constant is D minus C. You can figure that out by knowing what they have to undo each other. For example, T inverse of T of AX plus B is T inverse of A, A plus B, which is AX plus B, and you see that this is the identity, T inverse T is the identity on the vector space of polynomials. Now if you reverse them and do T inverse of AB, well, then you have what T inverse of AB is AX plus B minus A, and that gives you, putting it into T, the ordered pair AB. And you see that T inverse is the identity mapping on R2. Also notice, but we have not really proved it yet, that if you take these two functions that are inverses and get their maps relative to the two bases, I let beta be 1x, the standard basis for the polynomial vector space, and gamma be E1, E2. So the transformation matrix is, for T, is 0, 1, 1, 1, which now you know how to do, and the matrix for T inverse is negative 1, 1, 1, 0. Notice that when you multiply those together, you get the identity matrix. Let's prove that if T is a linear transformation and is invertible, in other words, keep in mind it is one-to-one and onto, then T inverse is linear. Because of lack of time, I might not usually put this proof in at this time, but I am going to ask you on your third minor to prove that some function is linear. So this is a good example. We know that T inverse is a mapping from W to V, and we want to show that it is linear. It's one-to-one and onto. So let's start like we would for any proof that a function is linear. Let W1 and W2 be two vectors in W, and let C be in our field. Now we want to show, I'll put a little thinking bubble up here. What we want to show is that T inverse of CW1 plus W2 is equal to C times T inverse of W1 plus T inverse of W2. That's what we hope to show. So we will start out with T inverse of CW1 plus W2. Since W1 and W2 are in W and T is invertible, we know that there exists, it's one-to-one, so there exists V1 and V2 in V such that T of V1 is equal to W1 and T of V2 is equal to W2. We also know that, let's write it down, since T inverse of W1 then is equal to V1, and T inverse of W2 is equal to V2. So that's information that we need. We have here T inverse of CW1 plus W2. So let's write it as T inverse of C of T of V1 plus T of V2. I want to get T into this conversation because I know T is linear. So now I can combine those two. I can say this is T inverse of T of CV1 plus V2 because T is linear. Oh, and T inverse of T is the identity mapping on V. So this gives us CV1 plus V2. And we know over here V1 is equal to T inverse of W1. So I can write C of T inverse of W1 plus T inverse of W2. And that's exactly what we wanted. Therefore, T inverse is linear. And this is an important result. If V is a finite dimensional vector space and T mapping V to W, a linear transformation is invertible, then the dimension of V is equal to the dimension of W. And I've written over here some things to keep in mind as we do this short proof, that T is one-to-one, it's onto, its nullity is 0. Oh, and there's one other thing we could write here. The rank of T is equal to the dimension of V. I'll just write dimension V. So we know those things because it is invertible. Okay, so let's start out with a basis for V. We'll say that the dimension of V is equal to n, and we'll call beta a basis for V, V1 through vectors V1 through Vn is a basis. Now, since that's true, we know that the span of the set T of V1 up through T of V sub n is equal to the range of T. And since T is onto, we know that it spans W. We know that the nullity of T is equal to 0 because the null space only has the 0 vector in it because t is 1 to 1. So we could say then that the rank of t, which is the dimension of v or n, is equal to the dimension of the range of t, which we have said is w. So the dimension of v is equal to the dimension of w. This is really important to know that if a linear transformation is invertible, that v and w have the same dimension, if that is, they have finite dimension. This theorem I am not going to prove. If v and w are finite dimensional vector spaces with bases beta and gamma respectively, and t is a linear transformation from v to w, t is invertible if and only if the matrix that represents t is invertible. Now, I think that you probably already knew that, but prior to this, we've been talking about the mappings, the functions, not the matrices. But here it tells us that, yes, the matrices must be square, because the dimension of v is equal to the dimension of w. It makes sense that t is invertible means that its matrix is also invertible. And in fact, the matrix for the inverse function is exactly. So this now will make isomorphism easier for you to find, because if v and w are vector spaces, we say v is isomorphic to w if there exists a linear transformation that is both 1 to 1 and onto, right? A homomorphism that's both 1 to 1 and onto is an isomorphism. In this case, it's a linear transformation that is invertible. Such a linear transformation is called an isomorphism from v onto w. So now if we just have a linear transformation that is invertible, or is 1 to 1 and onto, we know that it is an isomorphism. For example, this very simple one, taking R2 to the set of the vector space of degree 1 polynomials or less, the matrix for t would be, well, actually it's the identity matrix. So we quickly know that t is 1 to 1 onto and invertible, and we can conclude, therefore, R2 is isomorphic to, oh, I better not use, I'll write it out, is isomorphic to the space of polynomials of degree 1 or less. Soon we will talk about these less, and we will identify that as R2. And it's easier for us to work in R2 and study transformations of R2 than it is many of the other more abstract vector spaces. Let v and w be finite dimensional vector spaces over the same field. V is isomorphic to w if and only if their dimensions are the same. So we've already proved that if v and w are isomorphic, that their dimensions must be equal. So suppose that the dimensions are equal, and let's let beta be a basis for v, gamma be a basis for w. Notice they both have n vectors in them, and all we need to do is just create a linear transformation that is an isomorphism, that is 1 to 1 and onto. So it's very easy. Let's let t take v to w with t of v sub I equals w sub I. any vector in V can be written as a linear combination of the V sub i's, and the transformation just takes V sub I to W sub I, so it gives you the linear combination with the same coefficients of the basis vectors. This gives us a corollary that V is a vector space V, of course finite dimensional, is isomorphic to Fn. In other words, we could talk about Fn instead of V. We can identify the two vector spaces if and only if the dimension of V is equal to n. This is very important. It allows us to study vector spaces, finite dimensional vector spaces, from the standpoint of these coordinate vectors in Fn, instead of abstract vector spaces such as polynomial functions and matrices, etc. This diagram is in the text, and it kind of helps us connect the ideas of linear transformations and the representative matrices. So let's say we have V and W, finite dimensional vector spaces of dimension n and m. So we know now that V is isomorphic to Fn and W is isomorphic to Fm. So T is a linear transformation from V to W. We could also send V to Fn by this mapping that we have talked about before. Phi sub beta of any vector gave it its coordinates in Fn. You look back in your notes and you'll see that. And it sends each vector to its coordinate vector in Fn. Likewise, for the vectors in W, we have a mapping sending W to Fm. Phi sub gamma of the vector W is simply its coordinate vector relative to beta. So then we have a mapping from Fn to Fm. The author calls this LA, and because of lack of time, I left out that. It's the left multiplication by A, where A is the matrix for T. So let's just write Fn to Fm multiplication on the left by the matrix for T relative to the basis beta in V, gamma in W. And we called that matrix A. So L sub A just means that it is a mapping from Fn to Fm. It is an m by n matrix, and we multiply the vectors, these vectors here. We multiply those vectors on the left by A, and we get these vectors here. So you can think of mapping from V to W by linear transformations, or you can work in the fields Fn to Fm, and then your transformations are all left multiplication by the matrix representing the transformation. We did this problem in class. We found, we said T is a linear transformation from P3R to P2R done by taking the derivative. So we found in class that the matrix for that transformation was this one. Now, phi sub beta would take P of x. P of x is this. We're just looking at an example here. P of x is the polynomial 2 plus x minus 3x squared plus 5x cubed. So we could take P of x directly over by T to its derivative. Or we could transform P of x into, using phi sub beta, into its coordinate vector, and then send its we're going this way, in other words. Send its coordinate vector, multiply it by this matrix. Let's call this matrix A. We would take A and we would multiply it by that vector, 2, 1, negative 3, 5, and we would get this, which is the result that you would get by taking the derivative and putting it into its coordinate vector in R3.